Hello and welcome back to Rev Games Academy. In this video, we'll explore how to effectively manage game states using finite state machines, or FSMs, in Unity. FSMs are a powerful tool for organizing and controlling the behavior of your game objects, ensuring your code is clean, modular, and scalable. Whether you're creating player controls, AI behavior, or game systems, FSMs make managing transitions between states straightforward and efficient. Let's dive in. What is a finite state machine? A finite state machine is a programming model that organizes the behavior of an object into distinct states. Each state represents a specific behavior or mode of operation, such as idle, running, or attacking. Transitions between these states occur based on predefined conditions like a button press or an event in the game. For example, a player character might start in an idle state, switch to a running state when the movement keys are pressed, and then transition to an attacking state when the attack button is triggered. Why use FSMs in Unity? Using finite state machines in Unity offers several benefits that streamline game development. Improved code organization. FSMs encapsulate each state in its own class, making the code base cleaner, easier to read, and more maintainable. Scalability. Adding new states or modifying existing ones becomes straightforward and doesn't interfere with other parts of the code, enabling seamless expansion. And state-specific logic is isolated. Identifying and fixing issues is simpler, reducing the debugging effort. Reusable logic. FSMs promote reusability, allowing the same state logic to be used for multiple objects, such as players and enemies, saving time and effort. Let's walk through an example of implementing an FSM in Unity. In this example, we'll see a player character with 3 states: idle, running, and attacking. Here I have simple character with idle, run, attack, animation, and I have created some bunch of script for FSM we will see one by one. First, we see about base state class. The base state class serves as a blueprint for all states in the FSM. It ensures that each state class implements specific methods to define its behavior. This class contains an state enum, representing the state type, and provides the state key property, which uniquely identifies the state. And the enter state method is abstract and must be implemented by derived state classes. When the entity transitions into this state, the enter state method is called. It's used to initialize things specific to that state, such as triggering animations or setting variables. Like enter state, the exit state method is abstract and must be implemented in each derived state. It is called when exiting a state. This method is used for cleanup tasks such as resetting values or stopping animations that were initiated in the enter state method. The update state method is called every frame while the entity remains in the state. This method is where you put logic that needs to run continuously while the entity is in that particular state, like handling movement, animation, or other ongoing actions. And next we will see about state machine class. The state machine class manages the states and transitions between them. It ensures that only one state is active at a time and that state transitions occur smoothly. The start method initializes the state machine. It ensures the current state is properly entered by calling the enter state method of the initial state. This sets up the starting conditions for the state machine. The update method is called every frame. It checks if the state machine is currently in a transition state using the is in transition state flag. If no transition is in progress, it calls the update state method of the current state, allowing the state's behavior to be continuously updated during gameplay. The state transition method is used to switch from one state to another. It first calls exit state on the current state to handle any cleanup when exiting the state. Then it sets the current state to the new state, retrieves it from the state's dictionary, and finally calls the enter state method of the new state to initialize it. Now we see about player state machine class. The player state machine class inherits from the state machine class, managing the specific states of the player, such as idle, run, and attack. The awake method is called when the object is initialized. Here, the states for the player are added to the states dictionary. It maps each state enum, player state idle, player state run, and player state attack, to a corresponding state class, player idle state, player run state, player attack state. This ensures that all possible player states are available for switching. The switch state method is used to change the player's state. It accepts a state enum value, for example, player state ideal, and calls the state transition method from the base state machine class to switch to the new state. Now, player controller class. The player controller class is responsible for handling input and controlling the state machine of the player. In the awake method, the player controller instance is set up as a singleton. If no instance exists, it creates one, ensuring that the controller is globally accessible. This allows the controller to be referenced easily across other scripts. These methods correspond to specific player actions. When called, each method invokes switch state on the player state machine to change the player's state. For example, idle method switches the state to idle, run method changes the state to run, and attack method transitions the player to the attack state. Finally, player idle state class. The player idle state class represents the state where the player is idle and not performing any actions. The enter state method is called when the player enters the idle state. It triggers the isIdle animation in the animator component by calling setTriggerIsIdle. This ensures that the player's animation updates to reflect the idle state. The exit state method is invoked when the player exits the idle state. Additional tasks could be added here, such as stopping idle animations or transitioning to other animations. The update state method continuously runs while the player remains in the idle state. More complex logic could be added, such as checking for player input or conditions to transition to other states. The player attack state and player run state classes work like the player idle state class. Player attack state class triggers the isAttack animation when the player starts attacking. Player run state class triggers the isRun animation when the player starts running. That's it, guys. Now I can show you how the code works. And that's a wrap on today's video. We've covered the essentials of finite state machines in Unity, from setting up the state machine class to creating individual states like idle, attack, and run. As you can see, FSMs not only make your code more organized and scalable, but they also give you better control over your game's behavior. If you found this helpful, be sure to give it a thumbs up, and don't forget to subscribe for more Unity tips and tutorials. Drop any questions or thoughts you have in the comments below, and I'll see you in the next video. Happy game developing, guys!